as a radiation physicist, nuclear physicist. What's bad is, I think, the world that we're living in today, where you have nation states, non-state actors, proliferating, trying to build enrichment capacity, reprocessing capacity, missiles, you name it. And then the big global superpowers trying to develop better and better tools to kill each other, and hypersonic nuclear tip missiles, underwater autonomous drones, advanced nuclear weapons that have all these specialized capabilities.
Are you more worried about non-state actors or crazy state actors?
Whew. It's a good question. I always worry about, as these systems age, things happen, and when they're a system that might tell if there's an incoming attack, or that talk to nuclear weapons or units in the field, I don't know. It's a scary world.
Have my glasses on so I can read. Professional. That's how we're going to start this. Professional. Taylor Wilson is here.
All right.
A friend of the pod, a friend of Vice, a friend of Shane, if I might be so bold. A prodigy. We first met because when it was Vice and HBO, we were doing a show about energy. They were like, oh, there's this kid. He made a fusion reactor in his mom's garage. And I was like, what? So came out to see you. So when you went to the university, how old were you?
I was 14, yeah.
So you're Doogie Howser of the radioactive age. Saw the reactor, which freaked me out. Thank you very much, because I do have...
You're a little radiophobic.
I have radiophobia, yeah. Correct. And hung out. I remember three things from that trip, or our trips, let's say. One is wandering around the desert with you, pre-blowing stuff up, where you were like, yeah, uranium, you can just find it. It's stars that have hit the Earth. Of course, everybody knows, and you get this more energy because it's from a star.
This is a deposit of thorium and rare earths.
So this is a rare earth mineral.
Yeah.
And up in the hills, there's mines and old deposits of uranium.
They originated in some far-off galactic cataclysm, and they were deposited onto Earth.
And I'm like, I don't know that. I don't think anyone else knows that, which led to like the purest uranium in the world in Canada, and it's so pure that it has to run through. So uranium, you open my eyes. Two was blowing up stuff, which you're very good at. And three was making a star. So fusion reaction, which we're gonna start with, where we went to see the lasers.
Yeah, National Ignition Facility.
And they have ignition now.
Yeah.
So we have news. We have breaking news.
Yeah, finally put the I in the name.
Put the I in ignition. National Ignition Center, making a star so that we can have a fusion reaction. Yeah. Little star. And so anyway, friend of the pod, thank you for being here. Now, in full disclosure, I'm nervous. Because you're doing your own podcast. Yeah. Which is the reason why I'm nervous, is to have smart people who actually know what they're talking about doing a podcast is a threat to our jobs.
Maybe not.
Who likes going to the doctor? Not me. Now, whether it's a checkup or anything else you've been avoiding, ZocDoc makes booking a doctor stupidly easy. ZocDoc is a free app and website where you can search and compare high-quality, in-network doctors, read real reviews, and book instantly. They've got 100,000 plus doctors across every specialty. I've used it and it works. So go to ZocDoc.com/Shane and find and book a top-rated doctor today. That's ZocDoc.com/Shane. That's ZocDoc.com/Shane. This episode is brought to you by Zippix Nicotine Toothpicks. Zippix gives you a discreet way to get your fix. No smoke, no vape, just a toothpick. Come in a bunch of flavors, and they're proudly made here in the USA. Get 10% off your first order by using the code SHANE at checkout. Your lungs will be glad you did. Must be 21 years or older to order. Warning, nicotine is an addictive chemical. Zip more, smoke less with Zippix Nicotine Toothpicks. Bango. Tell me a little bit about the podcast, and let's get into what you've been doing.
Yeah, well, I mean, it's kind of what we were talking about. Like, when we met, you were doing a lot of climate change reporting on the HBO show. And I think we talked about it. It's like, you talk about these big problems for long enough without any solutions, and people kind of like tune out. They're like, the world's ending.
Which they're doing now.
Yeah, so that was the idea behind that, when you came and found me, is like, let's show what, the solutions are. And I think that's kind of the idea behind Giant Leap in a way, is like, Each
Sorry,
episode.
Giant Leap. Let's do it to camera. Giant Leap is the name of your podcast.
Yep.
This is called a plug in the industry.
Okay.
So Giant Leap, tune in, watch him. Scientists talking about science shit. Go.
But yeah, so each episode will be the future of a different topic. So, genetic engineering or batteries or electric aviation, you name it. And, talk to kind of the leading experts in these fields. And, I'm lucky that I've kind of gotten to become friends with a lot of these people who, are the world's leading experts in so many different fields. And, it's just kind of a conversation about, what the future of the world looks like, both the natural world and science and the technological world, and how we can solve some of the problems that we face.
Well, part of the cost for that plug is this podcast.
Okay.
Today. Shane Smith has questions.
All right.
Taylor Wilson, let's go.
Hit me with them. Yeah.
Ready?
I'm ready.
So we were talking earlier. Great to see you again.
Great to see you, Shane.
You make me feel smarter just by being around you. You've been in the desert.
Yeah.
Are you wearing it? You are. You've been in the desert with your Geiger counter. Have you been looking for uranium? What have you been doing in the desert? What's going on? And why were you in the desert?
Yeah, well, I was out in the desert hunting down different uranium deposits and rare earth deposits. Also hunting for samples of this new radiation biology project I've been working on.
Okay.
So looking for these highly radiation resistant bacteria that exist in the natural world and trying to figure out why they're there. And also the mechanisms they use to withstand, maybe 10,000 or 100,000s of times the dose of radiation that would, kill us.
Basically, every time you talk, I'm going to stop you.
Okay.
To explain what that means, because I'm not going to understand. So we're looking for boring uranium, which we always do.
Yeah.
But we're also looking for sort of biological entities that are very radiation resistant.
Yeah.
Why?
So, this project basically started as just a basic science, fundamental science, like curiosity thing of like, do these organisms exist? Why do they exist? And kind of anecdotally, going back to the 60s, we knew of them. There's this one Deinococcus radiodurans, which is kind of the type species of radiation resistance. And, just to put numbers to it, human beings, the LD50, or, half of the people are dead if they get this dose, is 500 rad. 500 rad.
LD50 is the lethal dose.
Yeah, for 50% of the population.
Right.
So we get exposed to 500 rad.
I'm dead, you're alive, probably.
Yeah, we're pretty much cooked. These organisms can withstand a couple million rad.
Wow.
And they keep on trucking. And at those kind of doses, their DNA, their genetic information is completely kind of like, severed and kind of sliced up. And so they have these ways to both do very efficient DNA repair, but also kind of scavenge the oxidative stress, these oxidants that are produced when radiation enters the cells. And so it started as just a basic science project of like, no one had ever systematically looked for these organisms. So going out and systematically looking in environments.
It's new, this is cutting edge stuff.
Yeah, it's fun stuff, but also, starting with that, but thinking about, well, are there applications for this? So yes, it's interesting from an evolutionary biology standpoint. Yes, it's interesting from an astrobiology standpoint of looking life, elsewhere beyond Earth. But if we can identify the mechanisms of radiation resistance, can we apply that to human health, make astronauts more resilient against space radiation, or
the Van Allen belt, which we'll be talking about. Don't think you're going to get out of it.
Okay.
Go.
But yeah, think like cancer patients that are undergoing radiation therapy. If we can make the rest of the tissues of the body have less side effects from the radiation therapy, that's great. So it's kind of, for me, the perfect mix of science. It's fundamentally curiosity-driven science that also kind of has an application. And now we have all these new tools like metagenomics and genomic sequencing where, in the 90s, we had the Human Genome Project, right? Multi-billion-dollar project.
To map
thousands of scientists to map the human genome, one genome.
Yeah.
Now we can, they're small, but these bacteria genomes cost maybe $100, maybe less to sequence their entire genome. And we can learn these differences between these organisms, what the genes code for, what, special things they might make, proteins, small molecules, you name it. So that's a fun project.
So I'm going to bring up this and you're going to laugh at me, but the little I know about this is because there was a debate, or there is an ongoing debate, that because tardigrades can withstand radiation and no water and atmospheric pressure and vacuums. Yeah. I think vacuums is the big one. that they could theoretically have traveled through space and come here.
Panspermia, or yeah.
And they're the aliens that we're looking for, the sort of tardigrades.
Yeah.
But the big thing was their resistance to radioactivity.
Yeah.
So, but we have bacteria that theoretically originates on Earth,
Yep.
that is resistant to radioactive pressure. So we can use that. How are we making that science a sort of usable thing for medicines?
Yeah, well, I mean, that's the translational piece, right? So, I'm doing all this work, going out, finding these organisms, sequencing their genomes.
Sorry to interrupt. How do you find the organisms?
Well, basically how it works is, I develop a set of hypotheses about where they might exist, like say a volcanic vent or a desert that has a lot of desiccation and UV. And I'll take a sample, an environmental sample, soil, water, moss, you name it, and blast it with radiation. So it's a sterilizing dose. Everything dies. But if there's still something left over, something that's still growing, then we use these, what we call culture-dependent techniques. We basically just grow these organisms. And then once we grow them, then we can do all the kind of mass spec and genomic sequencing and everything to understand, what are those mechanisms of radiation.
So you found them.
Yeah, finding new ones. I mean, no one's really ever systematically looked before. So, we talk about microbial dark matter, and it's this idea that, the majority of the microbial world is kind of unknown to science. We've identified a lot of the megafauna, the flora and fauna, the plants and animals of our planet. There's still a lot we don't know. But in the soil and the ocean and these kind of environments, there are literally, in a sample, thousands of organisms, microbes that do all these complicated things. And because we've never really had the tools, in the 20th century, we had very few tools to find these organisms. There's a lot there. And so the idea is, well, if some of those could be useful for applications, like in this case, radiation resistance, go and systematically look for them, culture them, or in some cases we can't culture them, but understand them and understand those mechanisms of resistance. And then there's the translational piece.
Yeah.
So okay, we have these mechanisms we can understand. They make a molecule that scavenges oxidative stress. Can we apply that to humans? And so we have some preliminary evidence in human cell lines that works. But there is a big gulf between that and, where we'd like to go to, which is putting this into, not only the kind of applications like making astronauts more resilient, but actual therapeutics for, cancer and for, preventing the side effects of radiation therapy. We were chatting earlier, but, things like radiation therapy destroys the salivary glands. That's horrible. If you have cancer and you get radiation therapy, it might save your life, but it has these terrible lifelong side effects. So can we target, for example, the salivary glands with these radiation-resistant compounds and make them more resilient to the therapy? That's kind of beyond my purview, as a radiation physicist, nuclear physicist. Yeah. But we hope that this will translate, to the clinic and hospital, eventually. And
are people working on that now, or?
Yeah, I mean, we're early stages of it. It's still pretty fundamental science at this point. But, I would hope that, as we learn more and more that, we'll start to hit that at least translational piece of the research.
Who likes going to the doctor? Not me. And unless you're into some bizarre types of medical fetishism, maybe not you either. Now, whether it's a checkup or a weird mole that looks like Elvis or anything else you've been avoiding, ZocDoc makes booking a doctor stupidly easy. ZocDoc is a free app and website where you can search and compare high-quality, in-network doctors, read real reviews, and book instantly. No endless waits. They've got 100,000 plus doctors across every specialty: mental health, dental health, primary care, dermatology, you name it. You can filter by insurance, location, ratings, and most people get in within 24 to 72 hours. There's even same-day availability. I've used it and it works way better than diagnosing yourself through Google. So go to ZocDoc.com/Shane and find and book a top-rated doctor today. That's ZocDoc.com/Shane. That's ZocDoc.com/Shane. This episode is brought to you by Zippix nicotine toothpicks. These days, finding a place you can smoke or vape feels harder than quitting. Zippix gives you a discreet way to get your fix. No smoke, no vape, just a toothpick. Perfect for any place where lighting up isn't an option. They're long-lasting, cost-effective, come in a bunch of flavors, and they're proudly made here in the USA, so no tariffs. Zippix have already helped hundreds of thousands of customers get their nicotine fix without needing to inhale, smoke, or vape. So what are you waiting for? Give your lungs a break and try Zippix nicotine-infused toothpicks. Ditch the cigarettes, ditch the vapes, get some nicotine-infused toothpicks at zippixtoothpicks.com today. Get 10% off your first order by using the code SHANE at checkout. Your lungs will be glad you did. Must be 21 years or older to order. Warning, nicotine is an addictive chemical. Zip more, smoke less with Zippix nicotine toothpicks. So I've written notes because that's the springboard to two different things.
Okay.
One is, you said dark matter, dark fauna, which is, I believe, been just coined right now, dark fauna. I love that. Dark meaning we just don't know that much about it.
No.
You know a lot about this, and I find it very interesting, and I think a lot of people are just sort of coming out of the pond and realizing that this is a thing. But maybe you could explain dark matter, dark energy, and how we came to sort of realize that, you know, we can measure planets and the math didn't work with, you know, gravity.
Yeah.
So Newton, you know, has to be rewritten because the planets weren't spinning off into, and that's led to WIMPs.
The Milky Way shouldn't hold together. It should just fly apart. And the particles we're looking for, these dark matter, we actually call them WIMPs. It's an acronym simply for weakly interacting massive particle. By weak, we mean that they will simply pass through the Earth and out through the other side. Only very occasionally, because of the properties of the WIMP, does it choose to interact.
So if you could give us a little primer on that, because I want to get into it, but I think that's, you know, a big topic in physics today, so let's get into it.
It is. It's exciting because it points to new physics, right? It's always that thing of like when something isn't right or something is missing, that tells you there's something new out there. And we're all, you know, as a physicist, that's exciting, right?
Yeah.
It tells you something new's out there. And you're completely right. A lot of it has to do with just basic things like orbital mechanics or observations. You know, we look out in the universe and we can tell some things. You know, we can tell, for example, the acceleration of the expansion of the universe, right? It's not slowing down. It's accelerating. So there must be, we think, although, you know, this is all within the bounds of statistical certainty, some kind of energy that must be propelling the universe apart faster and faster. That's what we call dark energy. Some of those estimates put that as high as, you know, over 90% of the mass energy balance of the universe is this dark energy, or what Einstein called the cosmological constant, this kind of fudge factor of like, you know, this missing energy, if you would. We say dark because it's not visible, it's not known. And then dark matter is what we think is the majority of the mass of the universe, based on observations, that is missing. So
you can't see it.
You can't see it. So
or measure it.
We can see obviously stars, right? And those form, you know, galaxies. We can kind of account for the more, you know, less luminous matter, the dust and the rocky planets and things around them. But you add all of that up, and then you look with a telescope at a distant galaxy, and you see the light is being bent by obviously gravity, right? Mass, gravity, the light's being bent. And you figure out how much visible matter is there. Well, it doesn't add up. There has to be something that's bending that light. We call that gravitational lensing, and you can see it's really cool if you look through a telescope at a galaxy and there are galaxies in between you that might be dark, you know, that might contain dark matter. You actually see these spherical aberrations, these kind of weird effects, optical effects. It's the light, we think, being bent by gravity. So we knew this, right? We've taken observations. We know there's this missing matter, potentially this missing energy. And so that leads to these searches, right? And it was fun for the HBO show. We did an episode on this, and you know, I got to go like a mile underground in South Dakota, Homestake Mine, where they have these big xenon detectors looking for WIMPs, weakly interacting massive particles that are just basically particles that have a lot of mass, but they never really bump into anything. So far, no luck. Still no luck. Literally nothing really that promising when it comes to WIMPs. We went.
So they're mathematically probable, but we can't find them.
Yeah, so we have something called the standard model of physics. And the standard model basically describes the particles and forces that we know of. So the leptons, I think like the electrons that are, creating the light here, the bosons, think all these things that we have, hadrons, protons, neutrons, those are the composite particles that have fundamental particles like quarks and gluons and electrons and muons. That's described in the standard model. We have to look what we call beyond standard model physics for these particles. And
Theoretical.
Yeah, in a lot of cases, they're theoretical predictions, which is fun. I'm not a theoretical physicist, but I, being an experimental physicist, need theoretical physicists to give us predictions that we can go and test. And then we either do one of two things. We do a hunt like those dark matter detectors underground in Homestake where you're shielded from the rest of the cosmic rays. Or we build big detectors like the Large Hadron Collider at CERN and smash particles into each other at very high energies, try to create new particles, look at what's missing, things like that.
So that's another springboard. Yeah. Let's talk about CERN because there's a lot of confusion about CERN and misinformation and disinformation. Yeah. So let's set the record straight. Yeah. What is CERN?
Okay.
What does it do and why?
Okay, so CERN, the European Center for Nuclear Research, Geneva, Switzerland, although the big one, the Large Hadron Collider, is mostly in France. It's, so big, it is in two countries. It's the world's largest particle accelerator, and a particle accelerator is just a way to take the particles, in this case protons or lead ions, but mostly protons. So think a hydrogen atom without electrons, take it up to 99.9999% the speed of light, very high energies. Think speed and energy is the same thing, kinetic energy, speed, it's all the same. So very high speeds, very high energy, and collide them into each other. And when you take these beams of particles and collide them into each other, you're creating particles. It basically creates a shower of mass from the energy that you've given those particles. And so we've done this since the first particle accelerators, going back to the 1920s, 1930s, really, the first electron or proton accelerators.
But what are we looking for it to do?
New physics and new particles, new forces. I mean, that's really what it is. And try to understand processes like the creation of the universe, right? So when you collide, for example, lead ions together in the Large Hadron Collider, this creates a form of matter called quark-gluon plasma. Quarks and gluons are constituent particles that make up all of the really matter around us. And we think that existed very early on in our universe. And so if we can recreate that process, well, maybe we can understand, how the universe kind of came to be.
Right.
Or we can discover new particles and forces. And so we've built bigger and bigger accelerators. Large Hadron Collider is, 17 trillion electron volt collision energy. So it's impressive how much energy is in that. But there are even more powerful accelerators, and those are the ones in outer space, natural ones. And so now there's very interesting physics going on looking at these high energy cosmic rays that in some cases are, maybe even an order of magnitude stronger.
So just to be clear, CERN is set up to study these, particle acceleration.
Yep.
It's naturally happening.
Yep.
So if we can figure out how to measure what's happening in space or coming from space, then we can learn more and not spend as much money theoretically.
Yeah, I mean, it's kind of a law of diminishing returns. As we build these bigger and bigger accelerators, you learn less as they get, progressively
bigger.
Pay
more, because I think they want to build a new CERN, which is like 21 miles around or something.
Which could be really cool. Yeah. But also, we have this physics we can do with the natural particle accelerators with cosmic rays. We were talking about this earlier, IceCube.
Yeah.
So
let's get into that. So for example, you have these cosmic rays. You can study. This is going to start about 48,000 conspiracy theories, as we say. Yeah. But there's a place in Antarctica that they're digging to try to get. So tell us about that. Because Antarctica alone is a conspiracy theory. And so the Antarctica and space and
hitting
CERN and everything. We're hitting 4.
Yeah. So basically, IceCube, it was an experiment that's been built in Antarctica in the ice.
Yeah.
So drill, maybe hundreds of holes into the ice and lower down sensors, in this case, just light sensors. As these cosmic rays come into Earth's atmosphere.
Sorry, who's drilling the hole? Is it America?
It's an American project, but it's an international collaboration.
International.
So kind of like CERN is, all these countries, similar thing. Most big physics is international collaboration.
Like ITER, which we're going to get to.
Yeah.
CERN, so this one.
Yeah. It basically sensors in the ice. And so what you see is as these particles enter the atmosphere and create showers or go through the ice, they create essentially, in this case, what is a sonic boom, but for light. So you've heard nothing travels faster than the speed of light. Well, in this case it does, but it's in the ice. So in a vacuum, nothing travels faster than the speed of light. But in a dielectric, in ice or water or glass, if you move faster than the speed of light, it basically sheds off light. It creates a cone of light, just like a plane traveling faster than the speed of sound. You pick up that boom, that cone of light, and you can figure out where that particle came from. That's IceCube, and it's incredibly cool because...
We have to go.
Yeah, I would love to go, yeah. But you think about how big, the Antarctic ice sheet is, and it's this, perfect medium for studying cosmic rays and high-energy particles.
But, I think about this a lot because, which I've got a lot of jumping around I want to do, but which can bring us, I guess, so we're sort of in France with CERN. We can stay in France with ITER. So we're here in Provence, the south of France, and that massive project over there is called ITER, which is going to be the largest and most expensive science project ever made. I was thinking about that when I wanted to talk to you, which is, if you could come up with unlimited energy, which we need more and more energy for everything.
Now we do, yeah.
But just crypto alone is
driving it, yeah.
So you've got crypto, you've now electric cars, and people are like, well, you still have to get the electricity for the electric cars. Were's that coming from?
Yeah.
So, and just growing population, et cetera, et cetera. Our thirst for energy is unquenchable.
Yeah.
And yet we're still burning coal, we're still burning oil, we're still burning fossil fuels. When you look at ITER, the philosophy behind it anyway, and fusion in general, of which you're intimate knowledge because you created a fusion reactor, which I want to get into at the end. But ITER, for those of us that don't know, is an international big collaboration for fusion. Creating a star, that puts out a lot more energy than it takes in. And once it goes, and it creates all this energy. Yeah. If that's the sort of North Star, if that's a possibility, the irony would be Texas, because it's oil for, so it's oil is funding the future.
Yeah.
But shouldn't we be going to be at the forefront of the tech for energy and fusion and alternative energy, et cetera?
Well, yeah, and I think that's our position as the remaining superpower. If we are that, is the one that funds this kind of, crazy moonshot, technology. ITER is exciting. It's an international collaboration. It's big, but we have projects here, even startups that are working on things like there's the company called Commonwealth Fusion out of Massachusetts, spinoff of MIT, and they're working on essentially same thing as ITER. It's called a tokamak. It was a Russian design of a toroidal confinement plasma device. It's a tokamak. But they're using these high-temperature superconducting tapes. They're have a very compact design, and it's possible they beat ITER to the punch.
Beat ITER to punch on a functioning.
Yes,
more energy out than in.
Yeah, a magnetic confinement fusion device that produces more power out than you put into it. This what we call technological break even. It's possible they'll beat ITER to the punch.
Right.
Because of, some improvements in technology and everything. And fusion is exciting now. We went, I don't know, really since the Manhattan Project, right after the Manhattan Project.
Which is fission,
to create the first atomic bomb. Edward Teller was a big proponent of the super. And so if you've seen Oppenheimer, Teller's portrayed, and Teller was really interested in, this idea of thermonuclear fusion, the process that powers the sun and all the stars in the universe. Could you essentially use a nuclear bomb, a fission bomb, to light off light fusion fuel, combine these atoms into heavier atoms, and generate a lot of energy. And sure enough, we did that in the 1950s. Ivy Mike and these very large thermonuclear tests in the Pacific created large amounts of thermonuclear fusion. And then people were like, oh, well, we went from the atomic bomb, 1945, to, the first nuclear reactors, the early 1950s, really, when the designs were made. Okay, then once we have the hydrogen bomb, it must be, less than 10 years and we'll have fusion power.
Fusion, right.
And it literally, since the 1950s, we have been trying and failing to...
Why?
Plasma's hard. So to get fusion temperatures sustained, you're at a state of matter that is known as plasma. Think of from temperature, solid, liquid, gas, keep heating it up, you get to plasma, where the electrons kind of dissociate from the atoms. A plasma is kind of what you need to hold on to. That's what tokamaks create, this toroidal bottle to hold, is really hard to hold on to. It likes to kind of squeeze out and trickle out the opening, so it's really hard to hold on to it. And every time we think we have it fixed, a new instability pops up. And there were competing approaches, throughout the 20th century. There's something called inertial confinement fusion. That's NIF, where we went, the National Ignition Facility. Kind of in a way simulating what Teller was doing with the hydrogen bomb.
And you let me know this after the fact, because I did, but the NIF was funded by naughty armament business.
Well, stockpile stewardship.
Yeah.
So Clinton, we had in the 1990s, the Comprehensive Test Ban Treaty, which was great because that basically said no one can test nuclear weapons, which is a really good thing for the world. It prevents, us from getting in a continuing arms race with China and Russia, testing bigger and bigger bombs that really have no purpose.
Huge rents in the ozone.
Yeah, exactly. Atmospheric testing is really bad because it, creates lots of fallout. But at the end of the day, nuclear weapons age, and, our security is in some ways based on these deterrents. Nuclear weapons is a deterrent. So if the president, presses that nuclear button for deterrence to work, you got to know the bomb's going to go off. And so we had to come up with a way, if we weren't going to test nuclear weapons, to be sure that as the plutonium ages, as the explosives age, as the electronics age, that the bomb's still going to go off. And so that's actually how NIF got funded.
Right.
It got funded as a stockpile stewardship program, being able to simulate or replicate the conditions of an exploding nuclear device.
Without exploding it, which is crucial. Yeah.
Any, actual nuclear
With no
bombs.
Bikini Atoll.
Exactly. But that allowed us to create a facility that we thought was big enough, again, simulating the exploding nuclear bomb with laser light, to ignite a pellet of fusion. And that'll never be a power plant. That NIF, that device, it's too slow, it's too expensive, the targets are too precise, it's too small. But the exciting thing is, for a while, I'll admit, I didn't think the National Ignition Facility would ever, I always joke, the national facility, would ever achieve ignition.
Yeah.
It's like we built these bigger and bigger lasers and we finally thought NIF was going to be it. And it looked like it wasn't big enough. But then we got some of the imperfections and the targets out, some of these instabilities under control, boosted the laser output a little bit, and finally got that ignition. So that means now we have a fusion device that can produce more power out than we put in for a split second, for the blink of an eye, but it does that. But that's exciting because I think hopefully that means we're entering an era, hopefully a couple decades, of burning plasma physics. Meaning, historically, all the fusion reactors we built, the energy that the reactor had was the energy we put in. Microwaves or magnets or, you name it. We had different ways of putting energy into the plasma. Well, now, hopefully, we're entering this era where the energy of the reaction is what's providing most of the energy. And that's exciting because that's a whole realm we've never been in, and that will inform new approaches to inertial fusion, new approaches to magnetic fusion like ITER and this Commonwealth fusion design, and this whole new set of, new is a relative word, but there's lots of new companies around really kind of the hybrid of the two. You call it magnetized target fusion, you call it magneto-inertial fusion. They're kind of hybrid approaches between what NIF does and what ITER does. And they may not work.
Right.
Some of them, most of them probably won't work. But if one works, that could be the holy grail.
Yeah.
It's just hard to do. And so I think And I say this very earnestly, very honestly, I think we're getting closer. And, in fusion, it's always the 30 years away and always will be. But I think we're getting closer. And once we have that, maybe it's another 10 years of engineering to make the design work as a power plant. But that will be an incredibly, I think, low cost, very safe, very sustainable way of generating electricity. Maybe not 100% of the world's power comes from that, but the base load power today
it's a game changer.
Yeah.
Now, why didn't that happen already? Like, nuclear energy got a bad rap. There's a lot, I think, media won. Movies, horror movies or not horror, whatever.
Yeah.
And there were a lot of bad things that happened,
Sure, yeah.
in Germany and here and Chernobyl, obviously.
Yeah.
But what happened? Like, why, we had this unquenchable desire or need for energy, and we're still using, the base, like, oh, here's charcoal. Like,
heat up the kettle.
Exactly. And so why didn't it work to date?
Yeah, it's a good question, right? I think, there was this dream of the atomic age, right? Coming out of the Manhattan Project, in the 1950s, the government had this big program called Atoms for Peace. It was the Eisenhower initiative.
Yeah.
And that had some unforeseen
fundamental flaws,
consequences, including what we were talking about earlier, some countries ending up with nuclear reactors that use that to, make a military program.
So that's an interesting point.
Yep.
It's designed for war, but the theory was, energy for everyone, freedom through energy, all this stuff, but just don't do anything bad with it.
Yeah.
And then everybody started
doing bad stuff
almost right away.
Yeah, and that was the fundamental flaw of Atoms for Peace, is I think Eisenhower and advisors thought that, if we basically gave the world, all the countries of the world, the tools of atomic energy, basically it would transform swords into plowshares, right? Take this power that destroyed Hiroshima and Nagasaki and generate clean energy and everything. And unfortunately, the story in the 20th century was a series of false starts. There's some things you don't want to do with a nuclear reactor, I think. You don't want to put a nuclear reactor in an airplane. You probably don't want to put a nuclear reactor in a car either. But there are some things you do want to do with a nuclear reactor.
Like what?
Powering communities, charging EVs, submarines. That one worked out really well. Makes for incredible technology of powering a submarine that can stay under the water for 6 months. Space nuclear power, getting us, out into the stars and giving us power when we're there. There's incredible applications of nuclear technology. Unfortunately, the 20th century was the series of kind of false starts. And one part of that story is we really focused on one type of nuclear reactor, and that was the light water reactor. This is the original, if you know Admiral Rickover, who was the head of the nuclear navy, invented the nuclear navy. He was a real hard ass, and he created the modern U.S. Navy that's based on nuclear power. That design essentially involved taking some uranium, making a reactor, pumping water through it, and you boil the water, turn to steam, turns a turbine, runs it back through. And there were some inherent limitations with that. That's what happened at Fukushima. In some ways, that's what happened at Chernobyl, although there were other factors of that design that contributed to it. But at the end of the day, light water is a voiding coolant, right? So it can boil away, and then you have no coolant. And in the process of boiling, it can blow the reactor apart. And nuclear power can be made, light water reactors can be made very safe. We probably won't have a nuclear, someone's going to take this in 20 years, a nuclear reactor accident at the scale of Chernobyl in this country because of the regulations, because we have such a safe industry around nuclear power.
Yeah.
But inherently, that light water, I don't think, is the perfect coolant.
What is salt?
Molten salt, maybe liquid metal, but molten salt and liquid metals are great ways to cool nuclear reactors. Yeah. And unfortunately, we kind of lost the momentum for nuclear power in this country around the 1980s, post 3 Mile Island, post Chernobyl. And that's not to say nuclear power plants today are unsafe. Again, because they're built very...
Also, we were using the byproduct, for weapons.
Yes.
So I think people were like, hold on.
Yes. There has always been this inextricable link between civilian nuclear programs and military nuclear programs. Yeah. Unfortunately, we're dealing with the consequences of that today with, problems in the Middle East and and elsewhere.
Hi, it's Shane Smith. Now, before we get back to it, I wanted to let you know about my new Substack. I'm shanesmith.substack.com. Now, I'm going to be posting a lot of new content there, from extended versions of this show to behind-the-scenes stories from my adventures all over the world with Vice. Now, the best part, it's free if you sign up now. So go to shanesmith.substack.com and enter your email. That's it, shanesmith.substack.com. Or click the link below, and now on with the show, which rhymes with Bazango. We have 75 things to get to, so let's keep talking.
Yeah, but anyway, so the idea is, nuclear power still has, I think, a lot of promise. I think maybe it's not that original vision of atoms for peace, but I think there is a future of nuclear power that, at least with fusion long-term, and fission is kind of the bridge, the stepping stone, we have the ability or the promise of producing, baseload, dispatchable, reliable electricity in a very dense way, without carbon emissions, without particulate emissions, without, having to go out and, contaminate the Gulf of Mexico with oil. We can do these things, and we can have a new generation of reactors that are much safer, that are passively safe, walkaway safe, this kind of stuff.
Didn't you, I think you were talking about, there's there's design for these small reactors that are molten salt, sort of fail-safe, no emissions, and they could do, like, for example, in Africa, where a lot of the forests are being burnt down to make charcoal because they're still relying on charcoal, which is, again, the most rudimentary way of doing energy, that you can have, like, these small reactors that are completely fail-safe, that you could have, like, per village and stuff. Yeah. Like, is that still a...
Yeah, I think that's the dream, right? Is that we create a very proliferation-resistant reactor that is very safe, that you could build in a factory, mass produce. I like to use the analogy of, and maybe it's become a bad analogy with everything going on with Boeing, but of like the aerospace industry, the aviation industry. If you go back to like the dawn of aviation, very risky business, right? They didn't fly very high. They weren't very safe. It's an industry that is very hard to insure because, you put a couple hundred people in a tin can, 40,000 feet, that falls out of the sky. That's a really bad day. But Boeing, and the kind of aviation industry was able to make airliners, mass produce them. Each one had the same design of a model, had the same design, had the same like quality control and regulatory oversight that made it very reliable and very safe. And it brought the cost down. Nuclear power never had that. Every nuclear power plant we built in the 20th century was a one-off thing. There were designs, but you would say, hey, we want to build a plant here in Alabama or Arkansas, and you would literally take millions of pieces out there and weld them up and build the reactor.
There was no scale, as we like to say today.
Yes, exactly. So if you think of economies of scale, one of the economies of scale is economies of manufacturing. If you build a lot of them, you can drive the cost down. But in doing so, you also, I think, increase the safety profile, the quality control, the technology, and all these things. So my vision, and I think it's hopefully becoming a reality sooner than later, is that we are able to make nuclear power in that way, in that Boeing model, the assembly line model, with a very safe design.
You're really choosing Boeing at the wrong time, my friend.
I know, I'm going to regret that. But that's
but overall, writ large.
Yeah, writ large, that idea of factory standardization of nuclear power at a smaller scale. I mean, this becomes challenging as you get to the very big gigawatt scale reactors. But certainly, anything from a microreactor down, say a megawatt, all the way up to maybe a couple hundred megawatts, something similar to like the combined cycle natural gas turbine generators that are, primarily the probably second, or in collaboration with renewables, the biggest source of new generating capacity today. If you could create something that's like that combined cycle natural gas plant, but doesn't use natural gas, which is expensive and variable and has carbon emissions and some particulate emissions, if you basically have a reactor that's a drop-in replacement for that I think really changes things. And I don't think that'll be 100% of the energy grid, because I personally think renewables and storage are really, really exciting.
Storage meaning batteries.
Storage meaning batteries, or pumped hydro storage, but batteries are taken off in a way that no.
Pumped hydro storage meaning you have, let's say, something like solar pushing the water up into the mountains, and then at night let the water out and it creates hydroelectricity.
Yeah. But it's crazy. I mean, in Texas, this whole idea of energy arbitrage has become a huge business because they have so much wind power in Texas, which is intermittent. So sometimes it's blowing, sometimes it isn't. And that doesn't always match when the demand is. So sometimes they have so much extra generation from these intermittent renewables like solar and wind that the price pretty much goes to zero. It just collapses. So some smart, people, business people are like, hey, if I set up some batteries, I can buy it for a very low price. And then when the price, skyrockets, when people are running their air conditioning and running their factories at the end of the day, I can sell that power back for, a huge, huge markup. So that's driving incredible adoption of storage technologies. And that's such a free market thing. That's not the government saying, hey, you have to do this.
Yeah.
That's just some smart people being like, hey, there's a business opportunity here. And that not only allows you to access more clean electricity, but it stabilizes the grid. And so I always hear these debates around, renewable energy and green energy and all this stuff. And it gets frustrating to me because, I think there's an opportunity here to create an energy grid that not only is cleaner from a carbon and particulate emissions standpoint, but is also better. It's cheaper and more reliable. Because, we talk about very large power grids, lots of nodes, lots of users, lots of generation, lots of transmission. Bad things can happen the way the system's set up today. And we've seen this at many times. It's happened over the decades, like in the Northeast, for example, where one fault can cascade through a power grid. And, whether that's an accidental fault, whether that's sabotage, you're talking about millions of people that hospitals and factories that no longer have power. So I think where we're going with the energy grid is a bunch of these smaller generators, a bunch of different kinds of generators with a lot of storage and a lot of edge devices, a lot of Internet of Things type devices on the grid. And that moves us from a place where the grid is inherently this very unstable thing that could fail at any point to something that's very robust, and a solar flare or a terrorist attack or something, it just keeps trucking.
So I'm with you, and I'm wondering why that's a sane answer, very rational. Why would there be any pushback against that?
Yeah, I don't know. As a scientist, I get frustrated by politics because it's ideological. As a scientist, I follow the data. As a scientist, I'm not wired to be ideological about things.
Are humans guilty of warming the planet?
Yes.
Okay.
I think so.
By the way, that's still a question out there for a lot of people.
Yeah.
So if that's the case, then renewable energy seems to be logical.
Yeah, and nuclear power.
The reason why I bring it up is I know that there's been a lot of money spent on this grid question.
Yeah.
Because, for example, Solar City, they were giving out free, by the way, Elon not only does great cars, but the best battery technology and the solar panels. Yeah. So the powers that be, i.e. old energy, were like, well, great, you can't get any more credits for being
feeding
renewable,
back into the grid.
By the way, should happen. And B, you have to you're not going to get credits for paying into the energy grid. Yeah. You now have to pay us because we need to upgrade
the transmission infrastructure,
upkeep of the grid. Yeah. So basically, and there was a lot of, let's say, lobbying and media money put up against it. So people are like, that renewable energy.
Yeah, it falls down on these ideological lines when it is, not maybe necessarily the true aspects of these technologies that we're kind of analyzing. And that's not to say that every technology has a trade-off, right? There are inherent challenges with renewables, right? There are inherent challenges with making enough batteries. There's inherent problems with all of these things. We need more turning, a turning capacity on the grid to keep it stable and to keep it in phase. But these are technological challenges that are very surmountable. And I just get frustrated when people are like, I just, I don't believe in whatever the technology.
So that's what I was bringing up, the belief system.
Yeah.
And you're like, well, I'm a scientist and this is what the truth is. And then they're like, well, I don't believe that's true. So therefore, if I don't believe it's true, burn all the coal you want.
Yeah. And, look, I believe that anthropogenic climate change is happening. Even if I didn't, there are reasons to not burn all the fossil fuels that we have. There's
So hold on. To go back to what you just said, anthropogenic. A lot of people don't know that.
man-made, human-caused climate change. I mean, that's the thing. Like, for me, it's like, the climate's always changing. You hear that from people that, might want to deny that climate change is happening.
Yeah.
Climate is always changing, and that's true.
Climate is climate. I mean, the Earth is.
Yeah, we can go back through the geological record, through ice cores, and see these epochs of human history that were wildly different than today. We could be sitting here in Malibu, either under ice or in a desert, and that is how the history of the Earth is because of volcanism, because of changes on our orbit or everything. But we know a few things about the era that we're living in today. And what are those things that we know? Well, we know that there's a large amount of CO2 that's released to the atmosphere from the burning of fossil fuels. We can measure that. We can look at the isotopic signature and see where that carbon is coming from and look at the levels. And we know in the laboratory that, when you have carbon dioxide and sources of heat, of infrared light, that it absorbs that and it traps it and it doesn't radiate out in space. And sure, these models are complex and there are things we don't know and there's lots of uncertainty. But if you look at the trends and the emissions and the heating and all of these things, we can start to put together a picture of what we're doing. And I think the most important thing is not that these are unprecedented in the history of our planet changes. It's that they're unprecedented in human history. And our ability to adapt to, it's the rate of change, it's the derivative, how fast things are changing. Our ability to adapt really is not near as quick as those changes are happening. And, that's all these things, that drive conflict, that drive migration, that drive shortages in resources. Those are the things I think we have to avoid. But again, take all that aside. Sure, maybe it's, this is, some other factor that's causing all this. There are still reasons to become a more technologically advanced, sustainable society.
But I'd like to get onto that. But
yeah.
I'd like to finish, though, with just a little slap on the hand.
Okay.
Scientists are bad salesmen.
Yeah. Yeah. No, it's fair.
Because I remember, I think we were talking about this, and I want to get back to this, but I was shooting in Greenland, which I want to talk to you about.
Yeah.
Greenland is melting, okay? And there was a ton of traffic on those episodes. And, there's never been more ice in Antarctica. It's just the poles are shifting, blah, blah, blah. And so I said, fine. I went to the anti-climate deniers, whatever, the anti-climate change, climate deniers conferences and listened to all their arguments, followed it, went down to Antarctica. And the scientists are like, it's melting as fast as it can melt. Yeah. And I'm like, well, that's not what they're saying over there. And they're like, well, there's always flat earthers. And you're like, that's 48% of America. I said that to him, the scientist, who was a big glaciologist, and he said, well, I'm a scientist, I'm not a salesperson. And I'm like, but you understand all of these things that you're coming up with, that the glaciers are all melting, that if these ice sheets in Antarctica break off, which they're proposed to do, it's 2 meters of sea level rise. 2 meters of sea level rise is a cataclysmic event globally, right? Because we live 80% of sea level. Yeah. So the sea level's gone. Yeah. Like it's 2 meters up. Yeah. So that the whole consensus of science thing just drives me nuts. Yeah. And the fact that scientists don't just say, look, there's always going to be 2 or 3% dissenting, but there is consensus of science. Yeah.
Well, and I think people fundamentally don't understand uncertainty. Uncertainty in science is so important. I love when there's new things to discover when I am not certain about something. Yeah. And uncertainty is part of the scientific process. Yeah. There'll always be error bars, statistical uncertainty with measurements that we make. But that doesn't mean that we don't know anything, right? You take a large enough data set and enough scientists and you kind of duke it out and you can kind of figure out the answers to a lot of these problems. But I think you're right. I think most scientists are very comfortable communicating with each other in professional forums, conferences, peer-reviewed journals, and everything like that. But because I think really as a consequence of the way that we have education in this country today and the siloing of the humanities and the sciences, they tend to not be great communicators, not in the ways that, other fields might, people in politics and law and the arts. So that's part of it, right? We need scientists and better forums for scientists to communicate with the public. And I think just in general, the more that the public kind of understands how science is done, the scientific method, about uncertainty and all these things, the better informed we'll be as consumers, as voters, as, patients, all these things. And so, that's part of this idea of Giant Leap, this podcast I've been working on, is like, how do we kind of like both create something that's entertaining, and inspirational, but also educational, not only in, what's going on in physics and biology and space exploration, but in what science is, right? Like, there's a great Carl Sagan quote about, and this was, Carl Sagan died in the 90s, but, we're moving into a society where we have all these amazing technological advancements, smartphones and space exploration and hypersonic aircraft, all this stuff that no one understands. We live in a society that is technologically advanced and incredible that no one understands. And that's not a good place to be.
AI.
Yeah. And not that everyone needs to be a quantum physicist, not that everyone needs to understand the minutia of how mRNA translates into proteins, but I think it does behoove us to understand our natural world and our technological world. And so Giant Leap hopefully will be a very small part of that, but we need scientists to kind of get out there, communicate what they're doing, communicate the uncertainty, and help people understand that, like, sure, yeah, there's a debate, and debate is important in science, but that doesn't mean that the consensus is necessarily wrong. It also doesn't mean the consensus is right. But the scientific method is embracing that uncertainty, embracing the idea that you could be wrong. And generally, when you're wrong, that's a good thing, because that means there's something we don't understand that is telling us there's new science here. And so I think that's an exciting part of science, is the uncertainty, but it's a part of science that most people don't, I think, appreciate.
Well, in this case, it's a get out of jail free card.
Yeah, for anyone that, has that kind of other agenda.
Yeah, they're like, well, there's no scientific consensus, therefore
right.
It's a question. You're like, well, there's pretty much scientific consensus that there's global warming that's caused by man. Which, by the way, you started off talking about that and then ended up saying, well, I love it when there's no consensus. And you're like, okay, that's exactly what I'm talking about. Yeah. Because there's people are going to go, see?
Yeah.
See,
Shane, he doesn't know. Yeah.
You bastard, you tried to put words in his mouth and he wouldn't even take it. So if you've made it through the smart, hard to follow scientific stuff to this part of the podcast, now we're going to get to the fun conspiratorial stuff. So IceCube, besides being a great rapper, is a scientific research station in Antarctica, which is not actually a fort built by the Rothschilds on the flat Earth. It is an actual continent.
As far as I know, yeah.
I've been there, and it is a continent. I've had people, like really smart people, say, well, what did you see there?
The continent of Antarctica is home to a host of surprising conspiracy theories like secret alien bases, thriving ancient human civilizations, a massive entrance to the hollow Earth.
What did I see there? I saw snow and ice.
I was in an Uber one time in New York, and the guy, he clearly wants me to know what he's listening to. He turns it up, and it's all this stuff about Antarctica being the bottom of the dome, and And he was like, oh, what do you do? And I didn't want to be, I'm a physicist. I kind of wanted to hear what he had to say. And I was like, oh, yeah, I'm a student or whatever. Yeah. And so I got the whole explanation of it, and it's fascinating. I mean, it's some of it is bonkers, but it's fascinating. Like, he was like, oh, I bet you, never known anyone that's ever gone to Antarctica. And I was just kind of kept my mouth shut. Oh, I bet you've never seen a rocket launch, because, they don't go up. They can't go up.
And they hit what is it? I
don't know. Oh.
Firmament.
And God made the firmament and divided the waters which were under the firmament from the waters which were above the firmament. And it was so.
Firmament, yeah. But,
which is a religious thing, which I didn't know. The firmament is sort of okay. So anyway, so we got Antarctica. So there's a belief, and you can explain the belief. What is the belief that's happening in Antarctica? The flat Earth belief that's happening.
Oh, I don't know that it's some kind of...
Oh, well, okay. So
you can explain.
Well, there's a lot. Well, first of all, the Earth is flat, but B, like Antarctica is hiding other continents, and there's other continents behind it, and that there's settlements there, and there's all kinds of things, and it's anyway. I've been, and I've flown over a lot of it.
Yes.
And it's a lot of ice, which, by the way, is melting. Now, that's the boring one, IceCube, which we're trying to build to find these cosmic rays.
Yeah, high energy particles from space.
Particles from space. There we go. Now, that's the boring one. The fun one is the Iceworm.
Yeah. Project Iceworm.
Project Iceworm. Yeah. I'm going to contemporize this by saying Trump wants to buy Greenland.
Uh-huh.
And there are a lot of reasons why Trump wants to buy Greenland, which isn't as crazy as you'd think. One of them being that the ice is melting. Therefore, there's all kinds of minerals, rare
resources,
resources that can be exploited. Because a lot of people, I don't know if people, the whole Viking misinformation campaign of Iceland versus Greenland. Greenland is not green. It's ice, and Iceland is not ice. It's green. So anyway, there's a story, the Iceworm project, which I really found fascinating. Explain what that is, because it's crazy.
Yeah, you were talking about going to Greenland. I was like, oh, we got to go to Camp Century. Basically, the long story short is that, we thought, oh, it might be a good idea to put nuclear missiles under the ice of Greenland, right? It's closer to Russia. They can kind of move under the ice undetected or whatever.
Which is wild.
Yeah.
Because it's 2 miles thick.
Yeah, and asked the Danish government, hey, this is y'all's place. Can we do it? And they said, absolutely not. So then we built.
So to be clear, the American government asked the Danes if we could drill holes in the ice to put our missiles nukes, and they said no.
Yeah, fair enough, right? And we're like, okay, well, let's still play this idea out. And so we built this. The cover story it's called Camp Century, and it was a scientific, age of exploration, scientific project to drill into the ice sheet, and make a underground, under ice, settlement that was powered by a nuclear reactor that had,
a settlement, i.e. for people to live in.
Yeah, and research and all this stuff. But it was, a cover for this idea of Project Iceworm, that maybe in this network of tunnels we could put nuclear missiles or whatever. And it was abandoned. This was 60 years ago. It was abandoned, and the reactor was taken away, although there was some small amount of radioactive waste and other refuse and everything, and it was buried in the ice, and they were like, oh, this will be safe for 100,000 years. No one will ever encounter this. And now, because the ice sheet is thinning, it's very possible that will start to reemerge.
So we buried all of our radioactive material under the ice. Some of it. And did we ever put missiles there?
No, that never got that far. I think, in the Cold War, there were a lot of ideas. I mean, ideas were, not in a shortage, but not very many of those were good ideas.
Right.
Even some of the things we did, like Operation Chrome Dome, where we had nuclear bombers in the air 24/7 being refueled, probably weren't the best ideas, because we had these broken arrows, where one of those happened in Greenland, where if you keep nuclear weapons on aircraft in the air all the time, occasionally they're going to crash. And we're lucky, and partly that's in the design of the nuclear weapons, but some luck comes into play in all these things. We never had a nuke flash. We never had an accidental nuclear detonation. We had a lot of broken arrows. We lost a lot of nuclear weapons, and we, contaminated Palomares, Spain, a fishing village, the Greenland ice sheet, and all this stuff. So, I in a way, I'm kind of disappointed that I didn't live in that era.
Right.
Because I'm so fascinated by Cold War history.
A lot of action was happening.
And so many crazy ideas were tried or proposed. I mean, we proposed nuking the moon, and we proposed, there was something called Operation Project Plowshare. And this was the idea of, could we find peaceful applications of nuclear weapons? So could we generate electricity by blowing up a nuclear weapon underground and pumping in water and turning it to steam? Could we frack natural gas wells with nuclear weapons? You can. It makes the natural gas radioactive. Yeah. But, that was...
Isn't there a theory or a plan or something that if you nuke Mars, it creates an atmosphere?
Yeah, I mean, that's something that Elon Musk has been a proponent of. But he has suggested that you could terraform Mars by detonating a whole lot of nuclear weapons at the poles, and basically taking that CO2, that dry ice and water ice, and pumping it into the atmosphere. I'm not personally a fan of that. I think, it makes sense to go and build a habitat on Mars. There will be incredible science we can do there. And maybe after that, we can start talking about changing the planet. There's too much good science to do there to, terraform it right now, I think.
Speaking of not understanding the science and all these things that are happening in nature, aren't there sort of reactors that exist in Africa
Yeah,
that
used
are
to.
natural reactors. Maybe what the hell's going on there?
Yeah, I mean, I love that because I think people think of nuclear physics, nuclear science as a very human-made thing,
Yeah.
you know? But in Earth's past, in a uranium deposit, old uranium mine today, an uranium mine in Africa, in Gabon, there were these natural nuclear reactors.
Sorry. It was an old uranium mine.
Yeah, it was mined in the 70s, 60s, 70s, 80s by the French to supply uranium for, the buildup of the French, nuclear energy empire. And they were mining this mine in Gabon and taking the uranium in. And they kind of had to measure the uranium when it came in to know how much of that one isotope, the uranium-235, the good stuff.
The stuff that, is popularized by weapons.
Yes, that good stuff. They had to know how much is coming in, how much is going out, do accountability for safeguards. They get a shipment in, multiple shipments in, and like most of the U-235 is missing. And they're like, oh, did this go to, so one of these nations that France was, in talks with or whatever. But some clever scientists figured out that, basically the missing uranium was burned up by a nuclear reactor in the ground. And it was a very rare set of conditions. The uranium-235 today is too small of concentration for it to work. But back then, because it has a shorter half-life, there was more of it. And there was water moving through the site that was very pure. There wasn't a lot of impurities that absorb the neutrons that initiate and control the chain reaction.
Which we make in heavy water.
Yeah, the Canadians were big fans of heavy water and exported that technology throughout the world.
Yeah.
But in Gabon, you could go down, dig down, and find the remnants of these old nuclear reactors.
So it's sorry, to be clear, it's naturally occurring high amounts of 235 and clean water that's going through. So it created a reactor.
Self-sustaining nuclear reactor. And we think it was periodic. So we think essentially what happened is the water would come in, the reactor would activate,
Heat up.
The water would heat up, the water would boil away, the reaction would stop, and it had this kind of oscillatory or periodic behavior to it. Think of it like Old Faithful, but, a nuclear reactor form.
Yeah.
And this operated for, millennia. It operated for a very long time. Of course, it's dead today, but that actually is a useful analog. People want to understand how to dispose of nuclear waste and ensure that, we can safely store it for longer timescales than humans have been around, much longer timescales. That's a hard challenge. Well, that happened there, and what we found is actually the products of the reaction, the nuclear waste of this natural nuclear reactor, didn't go very far. I mean, it basically, even though there was water and everything flowing through, those fission products, that waste material, was held on to the surrounding rock and clay very, very tightly. So it kind of informs how we design a repository.
I was just laughing because it's like nature's nuclear energy is better than ours. So like the marketing of it would be like, natural energy, natural.
Yeah, artisan.
Natural atomic energy.
Artisanal. Yeah.
Artisanal energy. Not to cut you off, but I want to stay on the conspiratorial stuff because it's fun. Let's talk about, and I brought this up with you, and I had a very long conversation at dinner with you, which you listened to very politely. Yeah. And then debunked in 2 seconds. And I want you to do it because I think it's interesting. I'm not a conspiracy theory guy, although what I love to do is hear about conspiracy theories and then say, okay, are they true?
Is there anything to it?
Let's look at it. Let's be investigative and go and figure it out. So I was born in 1969.
Great year.
One small step for man, one giant leap for mankind.
Just all of the evidence of we can't even get into low Earth orbit. We just can't do it. We can't get into orbit. Russians beat us. Soviets beat us. Right? And so we go, okay, we got to one-up them. So we're going to fly to the moon, hang out, film like dancing, and then fly back. Doesn't make any sense because we can't even get there, A. B, all of the, Kubrick made it. All of the shadows are wrong. It looks like a set. There's no stars in the sky. And my thing isn't even from those like technical things. It's like, okay, we didn't have computers, and all of a sudden they just fly up.
Primitive computers.
Very primitive. They fly up and then they land.
Hippity hoppity, hippity hopping over hill and dale.
by the way, didn't have computers. We couldn't shoot anything in 1960. We not only shoot it, we beam it back somehow, video, right?
Yeah.
Dancing around.
Yeah.
And the whole flag is waving, which it shouldn't be doing, all this stuff. But I'm just like, here's what did it for me is, okay, then we have to, okay, we've got a whole launch, thing, and that's the hard part and whatever. But then we launch from the lander, again, to come back to Earth.
Yeah.
And then have to hit a thing at precisely the right time that's orbiting the moon to get on to launch us back to Earth.
Yeah. Oh, it's incredible.
Now, the reason why it's gained credibility in my brain recently is because we've started to go back to the moon. And with supercomputers and with modern rocket technology and all these things, they're crashing, we're going to the wrong place, they're going to the dark side of the moon, and then we're losing them. Like, all of these catastrophes are happening. And it's 2025.
Yeah.
And in 1969, we did it flawlessly, went up there and then said, by the way, we did it. We're good. Never go again. And let's burn all the technology so we can't even go back and see what it was that we actually did.
Yeah.
Highly suspicious, my friend.
Okay, well...
debunk it!
All right, let's try to take it piece by piece. Well, I think the biggest thing I always tell people when it, people even jokingly bring up, the moon landing being fake, is we created incredible technology. We spent, so much money to create incredible technology. If we didn't do it, it would have been stupid, right? If we created, the biggest rockets in human history and the most advanced computers of their time, and these incredible tools of exploration, if we didn't go to the moon, that would have been stupid, right? To me,
not a great argument. How you debunked my argument is pretty good.
Okay.
And you did it again recently is, I've seen the moon rocks, which were, to explain what they are and how they're battered by radioactive.
Yeah, I mean, so we have moon rocks from the surface of the moon. Sure, you could have taken a robot up there, but that would have been just as technically challenging in 1969. And we can look at the isotopic signatures, the ratio of the isotopes in the rock, and understand that that's not Earth rock. It's been bombarded by the cosmic wind. It's, 4.5 billion years old and all of these things. So yeah, I've held moon rocks. I've also, in my collection have pieces of the Saturn V that are these incredibly engineered systems that, have the delta V that allow you to, do translunar insertion and go to the moon. I've even done things like there's, a retroreflector on the moon that was left by the Apollo astronauts, a pretty big retroreflector. And the reason we did that is because we wanted to make very precise measurements of the distance of the Earth and the moon. And you can take a laser on Earth and you can bounce the laser off those retroreflectors. And the amount of time it takes the light to get from here and back tells you very precisely the distance. And you can still do that today. Those retroreflectors are still up there from, the early, 1969 and the early 1970s. And so, yeah, and, the LRO, Lunar Reconnaissance Orbiter, is a newer mission where it's in orbit around the moon and can see those landing sites and everything.
So that's a big one.
Mm-hmm.
So now let's explain that a little bit. Okay, we now have a satellite orbiting the moon that's taking pictures of the moon.
Yeah.
And you can see the lander, which you couldn't see before up until now.
Yeah.
So it's there.
Yeah, but, very small object, very far away. And there's a lot of stuff left, that we can, kind of know is there, both by looking at it from Earth and also, from orbit around the moon. There's a lot of stuff left here on Earth, the hardware, the pieces of the remnant rockets, the moon rocks and everything like that. And to me, these are the two most incredible parts of the moon land, of the Apollo program. One is that we never lost anybody. The fact that we did, through Apollo 17, we sent people in, and look, the International Space Station, the science we've done in the last couple decades in low Earth orbit is incredible. Like this is, putting a football field size, hotel and laboratory and office in outer space in low Earth orbit is incredible. But the Apollo program sent people out into space, beyond the confines of Earth's gravity, of Earth's magnetic field, of, the proximity.
Through the Van Allen belt, which you have to debunk as well.
Yeah, I mean, there's radiation out in space, both trapped by our magnetic field, the Van Allen belts, and also galactic cosmic rays and solar wind at the moon.
that haven't been diffused by the atmosphere.
And the Apollo astronauts got pretty high radiation doses. That, I think, still is one of the most fundamental challenges we'll face going to Mars, is it's a long trip. And so we need to come up with better ways to the radiation biology work. Exactly.
We started with. See, that's what the
back
whole
full
service.
circle.
It's all a plan.
But from a conspiracy standpoint, that's not a reason that we didn't go to the moon. They got fairly high dose of radiation. If there had been a massive, solar flare, it could have been really bad. They could have gotten, acute radiation sickness in some cases. But anyway, so I think it's incredible that we did the Apollo missions without ever losing anybody. We got pretty close on Apollo 13. I mean, luck was very much on our incredible engineering, incredible ingenuity.
And luck. Because the Soviets lost a lot, and then we lost some, obviously, in the space shuttle.
Yeah, and we lost them, Apollo 1 was an incredible tragedy. And the fact that we came back from that and just, like that, we're able to rebuild the program and keep going is an incredible testament to that era. And at the end of the day, I think that's what it is. You talk about why we haven't gone back to the moon or why we can't go back to the moon, but at the time we were spending such a large fraction of our federal budget. So many incredible, talented engineers, literally tens of thousands of the brightest people America had ever made in, search of this singular goal laid out by a president who wasn't there anymore in his memory. It was an incredible national project. And, I think it's a shame that we didn't go after that. I mean, von Braun...
Yeah, like, why didn't we do bases on the moon? And
yeah, so von Braun had this all laid out. You can go back and look at the old, Disney films he did with Walt Disney, and he had it all laid out. I mean, the moon was, the first, and then, we would go to Mars. We had the hardware. We had NERVA, this nuclear rocket program, where we had these engines ready to go, ready to be mounted on a spacecraft that would tug us, propel us to Mars. We had the architecture in place for bases on the moon, bases on Mars, huge space stations, all these things. And then we beat the Russians. And then all the will fell away. Yeah. And Nixon was like, why would we spend a significant fraction of the federal budget on something we've already done? We've already beat the Russians. Russians weren't going to go to Mars. Russians could barely build a space station that didn't, kill their astronauts.
Right.
And that was what happened, was we lost the national will. And then in the 80s, late 70s and 80s, we transitioned to what was an incredible achievement, which was Space Shuttle and the International Space Station, and figured out how to live and work and build something as incredible as the International Space Station on orbit. But I think it's time that, we start to accelerate.
It was Cold War era. And the interesting thing about that is the period on that sentence is we threatened Star Wars, Reagan, threatened Star Wars, and the Russians went, well, we're done. And literally that was the push of Glasnost and Perestroika which is we can't compete, so
let's
over,
open up. Yeah.
Finally. Which brings us, and I want to thank you for indulging me. So you heard it here first. We did go to the moon, and you can see it with the laser on the thing that you've done yourself. You've seen the moon rocks. We can see the lander is there, et cetera. Okay, so we're putting one of the largest conspiracy theories of all time to bed.
Single-handedly.
I'm sure there'll be no comments about that whatsoever other than thank you. Mm-hmm. Now, are we entering into a new arms race? Because if you look at what's happening with Russia, by the way, let's talk about what happened recently with the Ukraine with the drones and speaking of our Chrome Dome, what is it?
Oh, yeah, Operation Chrome Dome.
Chrome Dome. Also, our, whatever they were, Stratofighters or whatever, I forget what they were, the old ones, B-52s, whatever. They were always staying. So their highest, most expensive, long-range tactical bombers were, I think, 2/3 of them wiped out by cheap homemade drones.
Incredible, yeah.
But the reason why I bring that up, A, is to contemporize it again, but also B, is... let's talk about that. But B, are we entering into, with this weird frenemy relationship that we have with Russia, also this non-frenemy, enemy, confrontational relationship we have with China? Obviously, North Korea is the outlier. And so, but we're starting to look for uranium again. We're starting this whole, process again. What just happened with Israel and Iran? Iran back in the nuke game.
Yeah.
Make some sense out of that for me.
Oh, well, there's a lot to cover there. Geopolitics is incredibly complex, and it's made incredibly complex by technology.
Yeah.
And in some ways, we're not in the Cold War of the 60s, 70s, 80s anymore. But in some ways, this, that was a bipolar world. This is a multipolar world, and it is scarier. Technological advancements haven't helped that. It hasn't made it less, it hasn't made it more safe from a geopolitical standpoint. Yeah. We think about things like missile defense and advanced deterrence and fighter jets and all these things. Hypersonics. And I just am not a believer that any of that, on balance makes the world a safer place. You change, there are asymmetries, you change the balance of power using technology. But I think inherently this all goes down to, it's not the technology, it's the people that control it and their personalities and their aims and ambitions. And I think the world we're living in now, whether you call it a new Cold War or not, is a very scary place from that standpoint. I think the more we can do to safeguard specifically nuclear technology, the better off we're going to be. And the more agreements we have where we can see what they're doing, they're open about what they're doing. Maybe they're not always open about what they're doing. We use spies for the rest of it, but we have agreements through like the International Atomic Energy Agency. Those are, I think, generally good things. Mm-hmm. What's bad is, I think, the world that we're living in today, where you have, nation states, maybe non-nation state, non-state actors proliferating, trying to build enrichment capacity, reprocessing capacity, missiles, you name it. And then the big global superpowers trying to develop better and better tools to kill each other. And that's both in Russia, where, they don't have a lot, but what they do have is a lot of investments into...
That's all they need.
Yeah, these big sabers, hypersonic nuclear tip missiles, nuclear tip underwater autonomous drones, things like that are very scary because... Sure, they're really cool and really new and really capable, but they're the kind of weapons you never want to use. So it's like, it's like a couple ICBMs and a couple of, ballistic missile submarines is a pretty good deterrent, when it comes to deterrence. This other stuff, advanced nuclear weapons that have all these specialized capabilities, I don't know. It's a scary world.
Well, speaking of a scary world, what just happened between India and Pakistan?
Two neighbors with nuclear weapons on the brink of war. India carrying out its deepest strikes inside Pakistan in more than 50 years.
Yeah.
To go back to Canadians love heavy water.
Yeah.
We came up with the can-do reactor technology.
On both sides.
On both sides, gave it to India and Pakistan, said, whatever you do, don't do anything bad with this stuff. De minimis amount of time. Like 2 years, 3 years later, they both had death.
Yeah.
There are no indications they're close to an escalation to a nuclear exchange, but that's always on the radar because once you're in it, it's hard to control.
But recently there's been I went to the line of control between India and Pakistan. The most militarized besides the DMZ in the world. They do that whole thing every day where, the mark. Terrifying because they're shooting at each other all the time and they hate each other.
Yeah.
They said if you go out on the bridge and you go one step too far, they'll shoot you. So this is the zero line right here in between India and Pakistan. If I go on that side, I can say goodbye to my toes.
But recently they've been shooting at each other and the rhetoric has been ramping up. And I remember I interviewed the ex-head of the ISI, the Pakistani I believe his name is Hamid Gul, general, and he said, I want to ride a atomic warhead into India. This is the head of their CIA, Dangerous, like crazy dangerous. And those are state actors. Now, just to add a little bit of sort of pedigree of your experience in this, you actually came up with technology to find stray radioactive material in ports using salt water, I think.
Yeah, with water. So I've done a lot of work around detection, and the nice thing about radioactive material or nuclear material is you can actually detect it. Unlike like a biological agent or a chemical agent, theoretically, it's tricky to do. You can kind of see it, and so a lot of that has to do with things like, how do you look at a nuclear weapon that might be coming in a port or across a border?
Yeah.
Some of that has to do, though, in a facility. how do you know what they're doing in that facility?
Right.
You know, if a country's declared this facility is like for civilian purposes or doing a certain thing, do we have the tools to make sure that they're doing what they say they're doing? Those are, I think, generally good technologies to bring to bear. It goes back to kind of what I was saying about, like, it's antithetical to folks that, you know, are generals and military planners and everything. But, like, the more open you can be about what your forces are, where they are, what you're doing,
capabilities,
the safer the world is when it comes to strategic weapons. You know, it's one thing, tactical weapons, people are going to shoot each other, whatever. But when we talk about deterrence, and we talk about the big ones, the ones we never want to use, I think the more we can kind of have eyes on that, have ways of knowing, and just being open about what's going on, the better off we're going to be, because, you know, there's, you know, uncertainty is bad everywhere. It's really bad when it comes to nuclear weapons.
So what's your biggest fear for where we are today, knowing obviously you're intimately sort of aware of, because you come up with the technology to find this stuff, of the threats? Like what keeps you up at night?
Oh, I don't know. A few things. Yeah, I mean, there's these a lot of threats. I think, you know, specifically when it comes to nuclear weapons, right? We've talked about some of the things, you know, the nation states that, you know, might have poor security of their nuclear weapons, or, you know, unclear chains of command, or, you know, degrading early warning systems. I mean, that's something that, you know, I always worry about with Russia is, and it's not just a Russia specific problem, but, you know, as these systems age, you know, things happen. And when they're a system that might tell if there's an incoming attack, or that talk to nuclear weapons or units in the field, you know, and the risk of accidents with nuclear weapons.
Which has happened.
Yeah.
There was a famous thing that happened in the 60s or 70s with a Russian physicist. By the way, physics saved the world. I don't know if you know that. There was a Russian physicist from who had his history in reactors. He was in the army. They had shifted him over to missiles, and he wasn't supposed to be there. Some guy called in sick, so they called him out of sleep and said, "Come in." And while he was there, their early detection systems lit up. And they said, go. And whoever the protocol was called the Kremlin or whatever, and they called the Kremlin, and the Kremlin said, go.
Yeah.
So we were supposed to have full-blown thermonuclear tactical war, and he didn't do it. He went against orders, and it turned out to be like a $2 switch had blown. He literally saved the world because, I don't know, he had some mathematical probability in his brain because he was a physicist. He could figure it out. And he said, it's not happening. And didn't flip the switch. Imagine if it was just Igor, strong like bull, smart like tractor. Like he would just gone, okay, I've been told to do it.
There are crazy stories in the Cold War on both sides. You know, the Iron Curtain. You know, crazy things. I mean, the height of the Cuban Missile Crisis. You know, there were nuclear weapons outside the traditional chain of command that were at the discretion of the captain of these fast attack submarines that the Russians had, escorting these missile boats down, or cargo containers carrying missile components down to Cuba. And it's one of those things where, you know, they have the decision authority. And unfortunately, nuclear weapons, once you start, it's hard to stop.
Are you more worried about non-state actors or crazy state actors?
Whew. It's a good question. I think I probably worry about accidents more than I think of intentional things. So that's probably more in the state actor category.
Yeah.
But, you know, it's all a worry. We were talking about this earlier, but it's these low probability, high consequence events. Yeah. You know, the odds of them happening are very low. It's like asteroid hitting Earth. You know, the odds of them on any given year is very low, but if it happens, it's really bad. And so I think it's worthy of investing a little bit of time in, trying to at least think about these and think about ways to deter against.
When I was growing up, non-proliferation was sort of on everybody's tongue, which made a lot of sense, which is let's dial back the lunacy of the arms race.
Yeah.
Because we had enough capability to destroy the world 30 times over, whatever. And so let's A, not proliferate, and B, let's reduce. So that just makes sense. That seems to have been forgotten.
Yeah.
And in fact, you know, during the sort of destabilization of the old Soviet Union, a lot of this stuff became a question mark, which is worrisome.
Yeah. No, I mean, everything you just said is true. And I think, unfortunately, and it goes back to openness and visibility, we used to have a lot of treaties. Think open sky treaties, SALT, START, intermediate forces treaties, all these things. And as part of those, like, it says, hey, we can have inspectors here and we can see what you're doing, and you destroy this bomber and put it out for the satellite to come over, and we're not necessarily in that world anymore. And I would hope, in my lifetime, we end up back in that world again, the world of the, post-Soviet, collaboration that we had with the Russians, but that's not the world we have today.
Well, what I worry about, what just happened in the Ukraine, and I was trying to explain it to my daughter, because they didn't grow up in the Cold War, as I did. And so I was like, well, it's not a real war, at the risk of now comments from, it's not a real war, because if you had a real war, you'd use all the weapons at your disposal. So I explained what the Ukrainians did, which is genius, but they built drones that are $5,000, $10,000 cheap, and they went after the most expensive weapons, the $100 million jets, and all over Russia, and sort of crippled 2/3 of it. Now, she's like, what do you mean it's not a real war? But you're like, okay, because they could retaliate tomorrow and they could nuke Ukraine and make it a parking lot. But then there's global condemnation. But if they wanted to win, like it was total war, like in World War II, using every weapon that you had, in fact, weapons that you didn't even have, you'd use, then they would retaliate.
Yeah.
And if they did that, they would win. And so now, there'd also be a pariah, and the Ukraine is physically connected to Russia, so it's the radioactive fallout and et cetera would be
very bad.
Very bad.
Yeah.
But these are things that you have to sort of keep in mind, because they are fighting a war.
Yeah, I mean it's something we all living in the atomic age, post Manhattan Project. War is different, and you always have to be cognizant that the final war is it's not good. It's not good for any of us. So I think it's all in our best interest.
So we've dispelled the world's biggest conspiracy theories and figured them out, which is good. We've talked about global security and non-proliferation and the biggest fears that we have in the world today. Good. Let's finish on what are the most exciting things happening in the worlds of mathematics and physics, science in general. Like, what's exciting out there? What's real? What, like quantum AI? What are you most excited about? What do you see happening? What's going on in the world of science?
I mean, there's so much stuff, and I think that's why, for me as a scientist, I love my job. It's fueled by curiosity, right? So you can just kind of ask questions and go down a rabbit hole. And we're entering an era where we have so many tools that even 20 years ago, people would have not even imagined were possible. I mean, a lot of it is around kind of big data. We now have, probably for the first time in human history, way more data than we have the scientists to kind of analyze it, around the brain, around cosmology, around biology, around physics, around all of these topics. Deep genomic sequencing, being able to, we were talking about dark matter, and we talk about dark matter and talk about, the physical concept of dark matter, dark energy.
And does dark matter, dark energy, does that turn physics on its head and redo the math?
It could. We don't know. I mean, that goes back to we have to admit what we don't know. And I'm not going to sit here and say, we absolutely know that there is some new particle out there waiting for us, or some new force that's going
Wimps are real.
That wimps are real. But we know what we don't know, and we don't know what we don't know. But some of the things we don't know, we know. And that is telling us that there is potentially new physics out there, and physics that'll help us do things like unify quantum mechanics and gravity. Einstein was not, even though he had the foundations, the photoelectric effect of gravity, there were things about quantum mechanics that just, made Einstein's hair stand on his head.
Right. He had a good tagline. But there was a lot of stuff in there that wasn't
Yeah, so
captured by that.
Yeah, so we're still, 100 years later, trying to unify the physics of the big, gravity, relativity, with the physics of the small, with quantum mechanics. And the quantum experiments that we're doing, the quantum experimental physics that we're doing is pretty incredible. You know, for Vice, we went to China, met Panjian Wei, looked at quantum key distribution to satellites.
So the countries start to think about trying something new so that maybe in the future we can be a leader.
Now we're entering an age of quantum computation that's very exciting. I think some of it's overblown, some of it's underblown.
How far do you think we are from functional quantum computing?
Yeah, see, it's a complicated answer to that question, right? Because people think quantum computers are like classical computers, that you'll have a quantum computer in your pocket that, whatever. But I think what we're closer to is demonstrating these quantum processes that theoretically exceed the classical computational capability. What we're a little bit farther from, and I think what is more exciting, is actually do something with a quantum system, let's call it a quantum computer, that is useful, that does something that a classical computer can't do.
Cure cancer.
Yeah, come up with a new material or some new insight into, a physics problem. I think we'll get there, and it's exciting, the advancements that are happening, and hopefully we will start to unify the disparate parts of physics that right now are, telling us different things. Obviously quantum mechanics and relativity, but within the fields of solid state physics and high temperature physics and low temperature physics, I think there will be some exciting discoveries. And we have new tools that we can bring to bear, like machine learning. I mean, machine learning is an incredible technology. It can find patterns in large sets of data that we wouldn't even imagine.
Incredible.
You can point a telescope at the night sky, unleash these forms of artificial intelligence on it, and it will pull out of that data set things we wouldn't even know to ask. So those things are exciting. Across physics, chemistry, biology. Going back to dark matter, we've talked about the physical dark matter. There's dark matter in other places, though, at least that I call dark matter. Talk about microbial dark matter, all of this unknown biology in the soil and in the atmosphere and in the oceans. We talk about dark matter in the brain. I mean, the brain is one of the frontiers of science that I don't know a lot about. I don't do that really in my day job, other than maybe a small relation to the imaging side of things. But it is fascinating, the discoveries I think we will make in the next decade about the human brain as we have new techniques.
I think most of my brain is dark matter. So what do you think? What do you mean?
Well, just understanding how the brain works, how these emergent phenomenon like consciousness come out of the neurobiology of firing synapses of glial cells and the biochemistry that makes up our brain. That's our understanding of that to, consciousness and complexity, and us having this conversation is a gulf that, as a curious scientist, incredibly exciting. I think one of the things for me personally that I'm obsessed with is astrobiology. The idea that, there is life elsewhere.
Our friends, the tardigrades.
Yes. Are they? Is panspermia real? But I think, it is a fascinating question. Not only that question of, are we alone?
Do you think we find some sort of life in your lifetime? Some sort of life?
Oh,
really?
absolutely. I think it's maybe even sooner than that.
Wow, where?
And I don't mean complex intelligent life, although that may be something we discover. But, in our solar system, whether it's the water moons of the outer solar system, whether it's the remnants of fossil life on Mars, I don't know, and I'll have to be convinced by very compelling evidence. But I think there's probably other genesis of life, in our solar system, or at least life that started somewhere and then spread. Because panspermia, that idea that there are these organisms that can withstand riding a piece of rock from one planet to another. So I think we will see that, and that's exciting because biology. We have the chemistry. We kind of know how you get from an early atmosphere that has maybe some CO2, maybe some methane, oxygen, nitrogen, to complex biomolecules, amino acids, and the proto-life, the prebiotic chemistry of life. And we can take, the earliest, what we call the Luca, last universal common ancestor, very simple life, and get to us, talking apes. But we haven't made that, that meeting between the prebiotic chemistry and biotic chemistry.
Yeah.
And astrobiology might start to tell us some things about that.
Hasn't there been something weird, and I'm going to make it even weirder, that they found something from another galaxy that is like radio transmission at certain
So
times?
There's a couple things happening. We have some radio signals that are weird, repeating radio bursts, things of that nature. There's even, in the search for extraterrestrial intelligence, SETI, those radio observations, some weird signals. None of those, just personally speaking for myself, none of those are super compelling.
Although I'm just going to say, the repeating radio one is funny. I'll tell you why. It's how Alien starts, the movie.
Oh, there you go.
It starts with the repeating radio thing.
Well, it was so funny because I got to meet Frank Drake, who started SETI, the Search for Extraterrestrial Intelligence, and has the Drake equation that, that describes the likelihood, the probability of life. And I got to meet him before he passed away, and he said something interesting. I thought, he started this 60 years ago, something like that, 70 years ago. And for, his entire life, he listened for radio signals, big dishes, listening out there for radio transmissions. Radio transmissions follow the inverse square law, or 1/r², which basically is just a mathematical way of saying things get very dim as you get farther away from them because they're going in all directions. Lasers are different though. You shine a laser, the intensity is, that collimated light, that intensity doesn't break down in all directions. And so Frank was like, we spent all this time listening for radio signals.
Should have been sending later.
But if today you were going to communicate with alien life, you wouldn't send out radio signals, you would send out optical laser signals. So that's like a shift in what we listen for.
Right.
And 100 years from now, there may be something different that we think of that we should listen for. So just because the cosmos are dark from intelligent life maybe doesn't mean they're necessarily dark.
Science shall set you free. You can hear about it on the Giant Leap podcast with the man, the machine, the legend, Taylor Wilson. Ladies and gentlemen, thank you for spending time with us.
Thanks, Shane.
When we find the aliens,
I'll let you know.
Come back and we'll talk about it and or anything else exciting.
Sounds great.
Thanks for your time, buddy.
Thanks, Shane.
Bango!
That was easy.
Easy peasy.
Didn't even draw any blood.